Hi everyone, I'm Samah, a master student under the supervision of Josh Zeevi. Now I will start with a brief overview about textures. So stochastic textures appear everywhere in nature, as we see here in this examples. And they can appear as a pure stochastic, as we see here, which look like a noise and randomly scattered dots. And they also can appear as a near stochastic, which incorporate also phase or edge-like information. And the main properties about this type of texture that they are Gaussian and self-similar in a statistical sense, meaning that the images in different scales share the same statistics. So therefore, they can be considered as an approximation of two-dimensional random process. And the main question, what is the suitable random process? So it has been shown that the fractional Perron motion, which is firstly introduced by Mandelbrot, is a suitable model for this subset of images, where it is firstly Gaussian process, and then it also self-similar in a statistical sense. So this process is well defined by a single parameter called the Hurst parameter, which define or control the roughness of the motion. So in our analysis for fully textured images, we first of all separate the image into two separated layers. The first is the structure layer, and the second is the texture, the pure stochastic texture, where the first layer is dominated by local phase. Therefore, if you randomize its phase in Fourier domain, we will see an observable distortion in the image appearance. However, if we do the same process and randomize the phase of the stochastic texture, we will not see any observable distortion in the resulted image. So let's compare between the two layers. In terms of phase, the structure layer has random phase, and it's almost uniformly distributed. However, the structure is dominated by local phase, as we see here in the statistic of the phase. In terms of magnitude, the first part, or the texture part, has a Gaussian statistic in wavelet's domain, in contrast to the structure element, which is highly non-Gaussian. Now I will show you two examples of application where this model can be used. The first application is classification of different classes or images belonging to different substances. So we first of all decompose the images into two separated components, structure and texture. We then extract feature related to both layers, the textural related features denoted by T, and we extract the structural related features denoted by S. We then perform classification using traditional classifier. Here for this task, we use the spectral clustering for this purpose. So as we see here, we get almost full separation between the corresponding classes. And indeed, the fusion of both structural and textural information is essential in order to boost the accuracy of the classification. Another possible method for using this model in X-ray imaging, for example, we use it for modeling and characterization of bone textures in X-ray images. So the main goal is to diagnose osteoporosis using X-ray images, where we classify between control and osteoporosis cases. And there are several challenges. One of them is that both control and osteoporosis cases show a high degree of similarity between them. In this task, we separate both texture and structure, And we extract features, as I mentioned previously, that are related to both layers, the structural and textural. We perform then the classification using classical SVM or other traditional classifier, and we see also here the combining between the features, the textual and structural information is also can increase the accuracy of the classification. So that's it.